Welcome back. In the previous video, we discussed the overall philosophy of this course and the importance of thinking like a hardware designer. In this video, we will formally introduce Verilog HDL, what it is, why it exists, and how it is fundamentally different from software programming languages. Understanding this difference clearly is essential before writing any meaningful Verilog code. What is Verilog HDL? Verilog HDL stands for Verilog Hardware Description Language. It is a language used to describe electronic hardware systems, particularly digital circuits. Using Verilog, we can model hardware at different levels of abstraction, from simple logic gates to complete digital subsystems. Verilog does not describe how a processor should execute instructions. It describes what hardware should exist. This hardware can then be simulated for functional verification and synthesized into real logic on an FPGA or ASIC. Why do we need a hardware description language? Modern digital systems are far too complex to design using schematics alone. We need a precise, text-based method to describe structure, behavior, and timing. A hardware description language allows us to describe circuits unambiguously. Simulate behavior before fabrication. Automatically generate hardware using synthesis tools. Verilog acts as the bridge between design intent and physical hardware. One of the most common mistakes beginners make is treating Verilog like C or Python. Let us be very clear, Verilog is not a software programming language. In C or Python, instructions execute one after another, under the control of a processor. In Verilog, there is no instruction execution in that sense. All hardware described in Verilog exists simultaneously and operates in parallel. There is no main function in hardware. There is no start or end. Once powered, the circuit is always active. So Verilog does not describe program flow, it describes circuit structure and behavior. Verilog allows us to describe hardware at multiple levels of abstraction. At the lowest level, we have gate-level modeling, where circuits are built using AND, OR, and NOT gates. At the next level, we have data flow modeling, where logic equations are written using continuous assignments. Then we have behavioral modeling, where we describe how the circuit behaves using procedural blocks. At the system level, we use structural modeling, where smaller modules are instantiated to build larger systems. In this course, we will move through these levels systematically, starting from gate level and structural modeling. Verilog serves two very important purposes. First, it is used for simulation. Simulation allows us to verify functionality, observe waveforms, and detect logical errors. Second, Verilog is used for synthesis. Synthesis converts synthesizable Verilog code into real hardware, LUTs, flip-flops, and routing inside an FPGA. Important warning: not all Verilog code can be synthesized. Some constructs exist only for simulation. A good hardware designer always knows the difference. This leads us to the most important principle you must remember throughout this course. Whenever you write a line of Verilog, you must ask yourself one question. What is the hardware that this line is creating? If you cannot visualize the hardware, you should not write that code. Synthesis tools are powerful, but they cannot fix conceptual misunderstandings. Tools assist the designer, but understanding drives correctness. To summarize, Verilog is a hardware description language used to model, simulate, and synthesize digital circuits. It operates on fundamentally different principles than software programming languages. In the next video, we will begin with the basic lexical elements of Verilog, identifiers, comments, logic values, and data types. Please review the syllabus and keep your textbook open as we move forward. Thank you.